Hi everybody, welcome back to Cosmos. There have been a couple of interesting videos lately about workshop demagnetizers. I'd like to show you a slightly different type of demagnetizer. So as usual, in horology or clock and watchmaking, the tools used for this kind of micro engineering are often a slightly different take on the usual workshop equipment that is found in engineering. So in horology, it's very important that the steel work, say particularly of watches, remains free of magnetism, because the parts are so small and light that even the slightest small amount of magnetism could cause erratic timekeeping, or even, for the watch to stop. And also because you can't really control where the watch lives or goes around on its owner's wrist. Very often watches will pick up magnetism from loudspeakers and lots of electromagnetic equipment around life. And so traditionally, or should I say, not traditionally, maybe for much of the 20th century or the latter half of the 20th century, most of the classic horological demagnetizers are just miniature versions of the typical demagnetizer which you might see around engineering workshops, which is basically a very strong electromagnet which you plug straight into the main, so it's got to be alternating current to work. And you then hold your part, or the tool that's become magnetized, like a screwdriver or files or whatever. You hold them near the body of the demagnetizer and slowly pull the two apart or separate them. The horological one works slightly differently. Well, actually, this particular type of horological one works slightly differently, and it's made by a Swiss company called Greniner. And the principle is pretty good. But before I open this up and show you how it works, just a word about how a demagnetizer actually achieves the effect of demagnetizing the component. And so, as I said, a classic demagnetizer will only work with an alternating electric current. And so what happens is you've got an electromagnet, which is a coil of copper wire, insulated copper wire, wrapped around a metallic core, which concentrates the flux from the electromagnet. And it serves to magnetize anything that comes within close proximity of it. But because the current is alternating, switching between positive, negative, positive, negative, positive, negative, 50 times a second or 60 times a second, depending on where you live in the world, the magnetism that's induced and in one half cycle will be counteracted and killed off in the opposite half cycle, because you've got the positive magnetic field, say the north pole of the magnetic field going through the work, and then suddenly you've got the south pole, and that will kill the field, but it will leave a new south pole in your tool. And so the idea is, as you pull the tool gradually away from the source of the magnetic field, these induced residual magnetisms will get weaker and weaker and weaker and weaker. Each half cycle, or every 1/50th of a second, new magnetism will be introduced, but it will be slightly weaker than the one that preceded it, until effectively there's no residual magnetism. And so that's the principle to bear in mind: a gradually diminishing strength of magnetic field. That is how you demagnetize any ferrous object that's been magnetized. And even in the earliest horological works, so here I've got an early edition of the Watch and Clockmakers Handbook, Dictionary and Guide by Frederick Britton, and this is not the first edition, but this is certainly a very old one. So this one's from 1907, the 11th edition, and so this book is still published now in a much revised version. And in fact, over here, under the heading magnetism, it shows an early type of demagnetizing tool. And in this box, in this little pillar-shaped box, and you can see the scale of it because there's a pocket watch resting at the top. And so the whole thing would probably be about, 5-6 inches high and about 3 or so inches across. Inside this box would be like a clock mainspring, and connected to the shaft would be a magnet. And you'd wind it up, and then when you're ready, you put the watch in the box, and when you're ready, you release the lock, and the mainspring releases, and the magnet goes whizzing round at a great rate. And you're meant to, well, actually, are you meant to pull the watch away? Let me just check. Under the title of Matador has been introduced an arrangement for demagnetizing as shown in the illustration. Oh yes. Okay, so there must be a gear train, because it says after being subjected to this influence for about a minute. So in other words, there would be a gear train, otherwise the spring will just instantly uncoil in a few seconds. After being subjected to this influence for about a minute, the watch is slowly withdrawn while the magnet is still revolving. So there again, the part being demagnetized must be slowly withdrawn from the magnetic field in order to work. And in fact, in this preceding chapter or paragraph, it describes that you could make your own demagnetizer by bolting a horseshoe magnet to the chuck of a lathe and revolve it very quickly. You'd want to have lots of clamps and things to make sure that the magnet didn't go flying across the room. Or particularly be able to spread out under centrifugal force. But that is an early type. But in fact, what I would have liked to show, and I don't know where I've seen the illustration, but it does exist, is of a type of demagnetizer that was basically a crank, like an old-fashioned telephone, and there was a magnet attached to the output shaft of that. And so you'd crank it by hand, and this magnet would whiz around, and then you'd withdraw your component out of that field. So moving on to really the best type of demagnetizer. This works instantaneously, or to all practical purposes instantaneously. By a single press of this button, that's it, demagnetized. So how does that work then? If you need a gradual weakening of the magnetic flux. So what happens here is, within this space, this angled space, there are two coils connected to each other, facing each other. So you're really well within the magnetic zone here. And you can see the little neon lamp. You can just see it flashing when I release this button. So when I depress the button, nothing. And then when I release it, you see the flash of the neon bulb. So that is thousands of volts passing through that neon bulb in a very short space of time. And so just to demonstrate, now I tried this earlier off camera and it didn't work quite as well as I would have liked, but it does work. What didn't work is I've got very, very fine shavings, iron filings, and I think I'd magnetized this screwdriver a lot because I used this little stack of rare earth magnets to magnetize. I don't want to bring them near to this pile of iron filings, otherwise I will never get rid of them. But you can see there's a little bit of residual magnetism on the tip of this screwdriver. So just to stop the iron filings going everywhere, I'm going to put it in this bag. And then, as I say, it seems to work gradually, maybe because the degree to which I've magnetized this very big piece of metal is much more than what this tool is designed to accommodate. So this tool is designed to demagnetize watch parts, which are tiny, very much smaller, thousands of times smaller in volume maybe than a tool like this. But it still demagnetizes, and in fact, you can feel a considerable force when the button is released. And there you can see that most of the fur is off off the screwdriver. In fact, if I just brush it, it kind of just falls off. So I'll do that again. I'll just remagnetize this tool. Right, so that's well and truly magnetized now. And if I look at that, it's got a nice beard. If I shake it, some falls off, but a lot does not. So I'll just put this piece of paper there and see if that increases the contrast. So quite a bit flew off there, and you can see now by just lightly shaking it, much more again. I think it's doing pretty well considering the amount of metal we're demagnetizing in a single stroke. So that's pretty good. So I've rearranged things slightly so that you can get a better view of what's happening. So I'll see if I can pick up any of these shavings. And I'll give it a tap. So I'm hitting it quite hard. I'll hit it with... You can see those iron filings are well and truly attached. I'll just tip these filings out of the bag because just to start afresh, and then we'll put the screwdriver back into the bag just to contain the mess. So there you can see I'll try not to particularly bias them in one direction or another. And I'll see if I can get rid of that glare. So now see how easily they fell away compared to a few moments ago. And it might help if I change the orientation of the tool. So look at that. We're nearly completely demagnetized. So there, we do have a tiny amount of fur. And if I tap it, I would say that is absolutely properly demagnetized. So that's the output. Like that's what it does, and it's simple, it's self-contained, and it's all in this kind of stylish 1980s looking box. I'm not sure if they still actually make this tool. You can definitely buy the normal ones, which are a little electromagnet with a push to make type of switch. So as long as you keep the switch depressed, the current flows. But I'm not sure if they make this type anymore. So I'll open it up so you can see the workings of this thing. I just wondered, while we zoomed in, you can see that neon bulb. Right, I better unplug it first. Just discharge the capacitor. Right, so there are 4 screws, 2 on the back. So there's one hell of a capacity inside here, so it's pretty dangerous even when it's switched off, because capacitors store energy for a very long time, like months, years even. And you can see they're pretty proudly made in Switzerland. Those were in the days when made in Switzerland really meant made in Switzerland, not made 40% somewhere else. The screws are longer than I remember. Let's go for a slightly smaller screwdriver. So the little data plate doesn't give too much info, just gives a serial number, type, 220 volts, 25 over 100. Don't know what that means. So yeah, anyway. And then we turn it back on its foot. Right, so there you can see the inner workings of this Greniner demagnetizer, MagnOmatic. So you can see a very sturdy capacitor, 16 microfarads to 10% tolerance. So it's a bit, a bit old-fashioned. In fact, I think it's definitely not 80s, because these components to me don't look like 80s components. And in fact, that fuse looks a bit puny. It doesn't quite fit the fuse holder, but hey, it works. And I've had this for many years. Never had to change the fuse. Well, I've probably just jinxed it. It'll probably blow the next time I depress the button. So here are the two coils, and you can see that they've got an iron armature that they built around, and it's a series of plates. In proper transformer practice, you've got a series of laminations, all stacked together, bolted together. So the purpose of having a series of laminations, why don't we have a solid piece of metal there? Because obviously a solid piece of metal is going to conduct magnetic flux better than plates, because there's going to be, microscopic gap on some level, even between tightly clamped plates. And the reason that we have these laminations or laminated plates is to, if my secondary school electronics lessons have served me well, I believe that it is to stop eddy currents from being passed from one area of the thing to the next, or to hinder the flow of eddy currents, which are induced electrical little swirling currents within a big block of material like that. And so actually it's more efficient and stays cooler. And at one stage I did trace the circuit a bit, not entirely, and I was quite impressed by this very chunky switch. So I have a close-up view of the workings. I'll just try and see if I can get that a bit brighter. Yes. And so really the current comes in through the fuse, through a resistor, red wire, into that terminal, which is normally closed. Oh no, sorry. That terminal is normally open, so the upper terminal back there is connected to this floating block here, which is normally open. And then the switch, which operates very smartly, it's a kind of toggle, so you can't kind of get it halfway, because it's got a, I don't know what that's called, it's a bistable blade. and when you press it a certain amount, it just springs into the opposite position. You can't kind of keep it halfway open or halfway closed. It's one or the other. And so in this position, the circuit is open, and when you depress it, you charge up the capacitor, and then when you release it, the capacitor dumps all its energy into those coils. And that is the key as to why you get the decreasing magnetic field, the rapidly decreasing magnetic field, which is so necessary to demagnetize something. It's all because of this capacitor. It's not about the amount of energy that the capacitor holds particularly, but it's about the way a capacitor stores and discharges energy over time, which is interesting for the purposes of demagnetization. And again, secondary school physics and electricity, well, I don't really need a sketch, but I think much better with a pen and paper in my hand. So the usual representation of a capacitor as a parallel pair of plates, metal plates, and a couple of wires going off, going to a power supply. And what happens is that between these two plates, and so the capacitor would in fact be a very long roll of thin foil separated by an insulating layer. But between these two plates, I'm using my left hand, an electrical field will build up. And you'll find that when there is no charge built up across the plates, the current actually flows very quickly. Or the current appears to flow very quickly because, current can't flow across an airspace. But the net effect is that there is a measurable current flowing. And as I recall, if you were to put this onto an oscilloscope and see the pattern it makes, or like the graph it traces as it's charging, you get a very quick charge as the current rises very rapidly and then tails off until it effectively stops rising. And as I remember it, it's fifths. I'd have to check. I should have checked before I made the video, but it's 1/5 massive rise and then 4/5 very slow. So for our practical purposes, we can ignore everything after that first rapid rise of charging. And the discharge curve is pretty much the same. So when the capacitor discharges, you've got a large amount of fairly steady current or charge, and then when you join the contacts, it plummets very rapidly. And it is this rapidly plummeting phase of the current flow that when dumped through that coil, creates a magnetic field that mirrors the pattern of this graph. So what you're getting is a massively strong magnetic field which rapidly tails off, but it is definite, measurable, and certainly decreasing over time. There's no part of this graph where any new section is the same value as the old section. It's a function. And so that is how we get the thing to demagnetize so rapidly, because you're getting a massive dumping of energy, but it is also tailing off incredibly quickly, within milliseconds probably, certainly, hundredths of a second at most. And so that's really the beauty of Swiss engineering. Look at that, this comparatively small market, but really a kind of perfect solution. And there's no guesswork involved. There's no, like how far away should I pull the tool, or how far away should I pull the watch, or the part, or the balance spring, or whatever from the magnet. And so that is your classic Swiss demagnetizer. I will just lightly reassemble this. And plug it in again. To test something more in the usual scale of what a watchmaker might use this tool for. And so that's a watchmaker screwdriver, 1mm. Oh no, that's a 1.2. So that's a 1.2 millimeter screwdriver blade of tempered steel, plain steel. I should say not stainless steel. I'll just put that back there again for contrast. And I will magnetize it. And this time I won't use the plastic bag. So we'll just magnetize that. So now that's got a nice beard. Okay, so that's about as much as we're going to get rid of in one go. And release. So that's mostly gone, and the rest might be because my iron filings are not particularly clean. You know, there's some greasy crud I picked up off my sawing machine. So it could even just be, you know, a bit of greasiness or oiliness that's keeping those filings stuck on there, because there's no tendency for them to jump back on. And if I draw this back through this area, well, it does pick up some, but it drops them again almost straight away. And if I put them back into these shavings, it does pick up a few, but they don't stay on. So really, it could even be the iron filings. It could be that these iron filings are magnetized, because don't forget that they are the product of a sawing process. And so even the act of reciprocating one piece of metal against another will magnetize both, provided they're both ferrous metals. And so these filings will be magnetic to some extent, because we've had this drawing action, reciprocating action of the saw blade against the steel. And who's to say that the parent steel from which this came was non-magnetic? And so all of those things, and I believe that that's the case, rather than this being magnetic, simply because of the completely pathetic way in which they just fall away. So it's almost like each one of those tiny microscopic filings has a magnetic pole, but because they're so light and small, it has no strength. Whereas if it was the blade that was magnetized, it would have a greater holding power. So I thought, just in concluding that chat, that I ought to really check whether my screwdriver was properly demagnetized. And so the way to test it, the simple way to test it, is to use one of these, which is a tiny little compass. So it's kept in a box like this, with quite a lot of space between the compass and the edge of the box, simply so that you can't get metal tools too close to it and affect the compass, you know, while it's lying in your toolbox or in your bench drawer. Or maybe it's to protect your tools from the magnetism of the compass, but I would have thought that the compass would be so puny and pathetic that it wouldn't magnetize anything if its life depended on it. Right, so how do we know if something's been magnetized? Because after all, any piece of metal will attract a compass. Any piece of ferrous metal will attract a compass. Well, of course, and the way the compass is behaving now, you can tell which way my bench is oriented. So if this tool is demagnetized, then it will equally attract either end of the compass. Well, no. So it definitely repelled the south pole of the magnet. Just let it steady. So the north pole is being attracted quite definitely. And if it were a normal piece of metal, the south pole would be attracted equally well. But it's not, it's repelled. So we know that there is some residual magnetism in this. And I know what this is. It's a piece of steel that I tested for hardness to see if it could be hardened. Because I was trying to make something. I think I was trying to make a screw which needed to be hardened and tempered. And so I've hardened that. And so I think really this shouldn't have any residual magnetism whatsoever, because when you heat something to red heat, it reaches something called the Curie point, which is when all ferromagnetism is lost. The magnet will no longer be attracted to a piece of red hot steel. And that's a way you can tell when the metal is ready to quench, by the way, if you're hardening steel, because if you stick a little magnet to it, the magnet will drop off when it reaches that Curie point, and that is also the same point that would be suitable for quenching. But this is a bit worrying because it doesn't seem to be attracting the magnet at all. Oh no, it is a little bit. Yes. Okay. So if I keep that the same way, I don't need to mark it because I can remember, but just so that for the sake of the camera really. Oh, that's completely invisible, but anyway, you'll have to trust me. So that side's facing south and attracting south somewhat, very, 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 very mildly. And now if I bring the same side round to north, north is also attracted somewhat. Or is it? I'll just turn it slightly around. Okay, so the attraction of this piece of metal is much less than the Earth's magnetic field, because beyond a certain point the magnet loses interest in it. So either it's a peculiar alloy. I'll just revolve that around. Yeah. Okay, so that is just a piece of completely non-magnetic material, not magnetized at all. Let's try to demagnetize our screwdriver just a bit more. See if we can get the performance a bit better. And really, the magnetic field is heavily concentrated within the zone, and so parts outside, you don't need to worry much because the flux is concentrated in that area there. Of course, there will be flux lines going around here, but they'll be much less concentrated. And remember, they're decreasing magnetic field. That's very interesting. Sorry, I've just spotted something off camera. I think because there's a chest of drawers below this bench, a metal cabinet. And I've just noticed that my magnet needle drifted round as I moved this. I don't know if that's even visible. But the magnet needle is definitely being drawn to all the metal tools and probably the metal of the bench itself. But if I put it more or less in the middle here. Right, so now we are attracting the compass to some extent. And then if I try the same on the other side, Now, does that constitute a repulsion? I think it does. Right, so the tool is still magnetized, but much less so than before. So if we try to attract the north pole of this compass, it's got a much less tendency. See, it doesn't want to follow it all the way around. So massive decrease in the amount of magnetism. Still some repulsion, still some attraction. One other thing to bear in mind is that the harder the steel, the harder it is to demagnetize. So the extreme of that would be ordinary cast iron. Doesn't stay magnetized really at all. It conveys magnetism very well, but it doesn't stay magnetized very easily. And similarly, hardened steel doesn't pick up magnetism particularly, but once it does get magnetized, it's much more difficult to demagnetize. Oh wow, so I think we've attracted the south pole of that magnet. Yes. And now the north. Yes. So that's it. We've completely demagnetized the screwdriver, and I know it's taken a hell of a long time and it wasn't that efficient. But I have been faffing around a lot, and I could have just given that half a dozen clicks and it would have worked. But the purpose is to illustrate a most unusual variation on what is otherwise a fairly ordinary piece of workshop equipment, the Watchmaker's demagnetizer.